pages, and today the title of today's seminar is Life and Work of Sofia Kovalevskaya, and on the second part, so 2/3 will be on the life and work of Sofia Kovalevskaya, and 1/3 will be Hilbert's 23 problems. I think you are aware of these two facts. I think you must have heard about Sofia Kovalevskaya. She is a Russian mathematician, and about the Hilbert's 23 problems. And behind this Hilbert's 23 problems. So I'll talk about this today. So these are all related with the history of mathematics, the struggle behind the development of mathematics. Let me first of all tell you about the 5 prominent lady mathematicians. There are a lot of prominent lady mathematicians, but I have chosen 5 of them. So let's remember 5 prominent lady mathematicians. One is Maryam Mirzakhani, 1977 to 2017. So you can see that she has a very short lifespan. The second one is Karel Keskulla Uhlenbeck, 1942. She is still alive. And Olga Ladyzhenskaya, 1922 to 2004. Fourth is Emmy Noether. I think most of you must have heard about this Emmy Noether, 1882, 1935. And then lastly, the Sofia Kovalevskaya. The concentration will be on the life and work of Sofia Kovalevskaya, 1850, 1891. So you can also see that she has also had a very small span of life, just like Maryam Mirzakhani. So I'll start with number 1. I think you must have heard about this Maryam Mirzakhani. So Maryam Mirzakhani, she is the only woman to win a medal, Fields medal. So up till this time, she is the only woman to win a Fields medal. So Fields medal is a very prominent medal given to mathematicians below the age of 40. And is given during the International Mathematical Union opening ceremony. Especially, generally it is given by the head of the state, where the International Mathematical Congress hails. So Mirzakhani was awarded the Field Medal in 2014 for her outstanding contribution to the dynamics and geometry of Riemann surfaces and their moduli surfaces. The award was given in Seoul at the International Congress of Mathematicians on 13 August 2014. So this is the photo when it was given here. Actually, I took this photo. The President of the Republic of Korea, Park Geun-hye, presenting the field medals to Maryam Mirzakhani. So Maryam Mirzakhani is from, of course, she is by citizen, she is Iranian. And this time it was a very rare coincidence of 3 females. You can see 3 females over here. The President of the Republic of Korea, Park Geun-hye, the first female field medalist, Maryam, is here. And at the time, President of International Mathematical Union, which hails the International Congress of Mathematics, under which the International Congress of Mathematics takes place, is Professor Dr. Ingrid Dovbegik. She was the president of IMU at the time. You can see this is a very rare coincidence that the prominent 3 people, the field medalist, the one who gives the field medal, awards the field medal, and who organizes ICM under the International Mathematical Union, there were all 3 females. Now we know that she is no more. In no more in the sense that she is no more president. She has been outstated there. And of course, she also has passed away. But Ingrid is still there. But she is no more president of International Mathematical Union. So it's a very rare coincidence. So, wait, okay. The other 2 on the these 3 gentlemen also, they are also recipient of field medal at the time. So, Maryam Mirzakhani is the first female field medalist. The President of the Republic of Korea, Park Geun-hye, the first female field medalist, Maryam Mirzakhani is here. And at the time, President of International Mathematical Union, which hails the International Congress of Mathematics, on which the International Congress of Mathematics takes place, is Professor Dr. Ingrid Dovbegik. She was the president of IMU at the time. You can see this is a very rare coincidence that the prominent 3 people, the field medalist, the one who gives the field medal, awards the field medal, and who organizes ICM under the International Congress of Mathematics. So it's a very rare coincidence. So, So I was present there as the president of Nepal Mathematics Society. We're in the second row with my wife, you can see, very close, so that I could take a lot of photos there. So after applauding, after she received the award, so Maryam Mirzakhani, she is from Stanford University in USA. She's working over there. She worked over there. So it was given for outstanding contribution to the dynamics and geometry of Riemann surface and their moduli. So the material work of Maryam Mirzakhani is simple loops on CTX, complex geodesics in MG, and she also worked on earthquakes. So let's have a brief biography of this Maryam Mirzakhani. So she was born on May 12, 1977 in Tehran, Iran. So she is from Iran. She was the first student in her all-girls high school in Tehran to participate in the International Mathematical Olympiad, IMO, where she became the first Iranian to win 2 gold medals, achieving a perfect score in 1995. And unfortunately, Maryam Mirzakhani birthday, May 2012, is declared World Day of Women in Mathematics. So ladies mathematicians should know that May 12th of every year is now celebrated as World Day of Women in Mathematics. And so our Nepali female mathematician also should now observe May 12 as the World Day of Women in Mathematics. She was a mathematician and also a professor of mathematics at Stanford University. I have already shown that. Our research topic included T.H. Miller theory, hyperbolic geometry, ergodic theory, and symplectic geometry. She died on July 14, 2017, at the prime age of 40 in Stanford after a 4 years battle with breast cancer. When she was in Seoul, we already knew that she has a breast cancer. So a lot of participants over there were discussing about the breast cancer of Maryam there. And on July 14, 2017, when she passed away, I was in Brazil, Rio de Janeiro, participating in the International Mathematical Olympiad. I was attending the jury meeting of IMO. So jury meeting is held just prior to the competition, where the final questions are selected. The final 6 questions are selected for IMO 2017. So I was there, and also we were having tea on 14 July with this is our team leader Deepak and Mahendra Panti, who is now residing in Brazil. He's our professor in mathematics in Brazil over there. So we're having tea when we heard the news that she has just passed away on 14 July 2017. So that was Marian. Now the other one I have mentioned is Karen Kesul Uhlenbeck. She is the first female Abel laureate 2019. The Abel Prize was given for 2003. In my first introductory lecture, I have shown the photos where Abel Prizes were given. I was present there in 2005 and 2007. So the Abel Prize for Karen was for her pioneering achievements in geometric partial differential equations, Gauss theory, and integrable systems, and for the fundamental impact of her work on analysis, geometry, and mathematical physics. Generally, this Abel Prize is given to person who works on varieties of mathematical disciplines and try to combine them in some way, or find a link between the various mathematical disciplines. So this is the photo when Karen got the Abel Prize in 2019. The prize, as I have told, is generally given by the King Harold of Norway itself. The Board of Norwegian Academy of Science and Letters has decided to increase the prize amount for the Abel Prize from 6 to 7.5 million Norwegian crowns the same year. So before that, it was 6 million. When Karen Kesul got the prize, it was 7.5 million instead of 6. Karen Kesul was born in Cleveland, Ohio in 1942. She is American. She earned her PhD degree in mathematics in 1968 from Brandeis University in Waltham, Massachusetts. She held position at several universities before settling at the University of Texas at Austin in 1987, where she stayed until she retired in 2014. She is retired, but she still works on mathematical discipline. So Karen Keskulla was the first plenary speaker by a woman in Annual Congress of Mathematics in 1933 in Zurich, Switzerland. She was also the second ICM plenary woman speaker at the 1990 ICM held in Tokyo, and was delivered 58 years ago. You can see first lecture she had at ICM was in 1932, and the second one was in 1992 after 58 years. So that means she was so active in mathematics during this close to 60 years. Now, another lady mathematician is Olga Ladyzhenskaya. Olga Ladyzhenskaya was a Russian mathematician who worked on partial differential equation, fluid dynamics, and finite difference methods for the Navier-Stokes equation. Now, all of you must know that Navier-Stokes equation is such an important equation, which is the basic for mathematical modeling of many problems or phenomena. And when I had my first PhD candidate, Dalbar Adhikari, so Dalbar Adhikari worked on partial differential equation, and she used a lot of these her mathematical methods over there. Graduated in 1947 from Moscow State University. She received her PhD there in 1951 from Leningrad State University. She graduated from Moscow, that is master's she got from Moscow, but the PhD she got from Leningrad State University. Now it's called Petersburg. She received a second doctorate from Moscow, and again in 1953 she also got a second doctorate degree. Generally in Russia, after PhD they do DSc, Doctor of Science, they call it. So she has both the degrees of PhD and DSc. She is the author of more than 200 scientific works. You can see how many works, how much lot of works she has done. Our work on 19th century Navier-Stokes equation helps meteorologists figure out the path of storm clouds, among many other uses. So I have told that mathematical modeling is based generally on Navier-Stokes equation. She was on the shortlist for potential recipient for the 1958 field medal, but she didn't get it. She gave a special Noether lecture at the ICM 94 meeting in Zurich on August 4, 1994. The mathematician died in St. Petersburg, that is Leningrad in the earlier time, in 2004 at the age of 81. In a New York Times tribute or obituary, New York University mathematician Peter Lax, who is also a Abel laureate of 2005, said she was also always a rebel and treated as one of the Soviet government. Now, Emmy Noether, 1882, 1935. Emmy Noether, she is a German mathematician whose innovations in higher algebra gained her recognition as the most creative abstract algebraist of modern world. So as one of the leading mathematicians of our time, she developed the theories of rings, fields, and other branches of algebra, modern algebra. In physics, Noether's theorem explains the connection between symmetry and conservation laws. So she also worked in part of physics. At the time, women were largely excluded from academic positions. So this is the beginning of 19th century. In 1915, she was invited by David Hilbert and Felix Klein to join the mathematics department at the University of Göttingen, Germany, a well-renowned center of mathematical research. Emmy Noether was the first woman invited by International Mathematical Union to deliver a plenary address at the International Congress of Mathematicians in 1932 in Zurich, Switzerland, as her algebraic acumen was recognized around the world by that time. Emmy Noether died on April 14, 1935, few times after doctors discovered a tumor in Noether's pelvis. The Association for Women in Mathematics holds a Noether lecture to honor women in mathematics every year. The crater in the moon now called Noether on the far side of the moon is named after her. So there's a crater in moon which is named after Emmy Noether. Now coming to Sofia Kovalevskaya. So I went to Rio de Janeiro for ICM 2018, the last ICM, I should say, 3 years back. So I participated over there, and there you can see in room 2006A was my presentation on the Sofia Kovalevskaya and with the title and the Prix Bordin. So this presentation which I have given in ICM 2018, so I am using that slide to tell on the life and work of Sofia Kovalevskaya. So the title over there was Sofia Kovalevskaya and the Prix Bordin. So the ICM 2000 was held on August 1, 2018 in Rio de Janeiro, Brazil. So this is my presentation over there. Now I'll go to life and work of Sofia Kovalevskaya based on the presentation at ICM Rio de Janeiro, Brazil, August 1 to 9, 2018. Now the biography of Sofia Kovalevskaya, 1850-1991. So she lived only for 41 years, you can see. She was the first woman in modern Europe, the whole of world at a time, to gain a doctorate in mathematics. So she's the first doctorate in mathematics lady, the first to join the editorial board of the scientific journal, and first to be appointed professor of mathematics. You can see what a prominent lady she was within these 41 years. So she was the first to get a doctorate degree in mathematics. She joined the editorial board of a scientific journal, about which I'll tell later on also. And she was appointed the first professor of mathematics in Europe, as Europe was the most prominent center of mathematics at that time. So you can say to the whole world. So that's her photo. So when I went to study in Russia, when I joined mathematics department, then in the department, on the lobby of the department, and in other universities, just like Moscow University, where I also had 1 year's, during my PhD, 1 year's seminar course there. So I saw her photo on the walls everywhere, and I saw this type of photo, always a very young face. Only later on I found that she died at the age of 41. That is why all her photos are of this prime age. Her groundbreaking work in mathematics made her male counterparts reconsider their archaic notation of women's inferiority to men in such scientific areas. So she was no inferior to any male mathematicians. Sofia Kovalevskaya was born on January 1850, Moscow, Russia. Sofia Kovalevskaya was a middle child with an elder sister. She has an elder sister, Anya, and brother, Fedya. Father was Vasily Korvin Kurkowski, an artillery general. Mother was Elizabeth Subet. She was a well-educated member of Russian nobility. So she was from the noble family. The photo of father and mother is there. Childhood. Sophia's exposure to mathematics began at a very young age. When Sophia was 11 years old, the walls of our nursery were temporary for a shortage of wallpapers, papered with pages of Ostogradsky lecture, Russian mathematician, lecture notes on differential and integral analysis from her father's university days. So you can see she has seen some formulae, mathematical formulae at the age of 11 years. Sophia credits her uncle Peter for first sparking her curiosity in mathematics. When 14 years old, she taught herself trigonometry in order to understand the optics section of a physics book that she was reading. So I don't have the photo at the age of 14, so I have the photo at the age of 16. After concluding her secondary school in St. Petersburg, though she was born in Moscow, but she lived most of the time in St. Petersburg. In 1867, she was determined to continue her education at the university. Russian universities in the 19th century were closed to women. So in the 19th century in Russia, you can't, women were barred from joining the university. Women in Russia could not live apart from their families without a written permission of their father or husband. So she should get a permission from her father or her husband. So at the time she was still not married. To resolve the problem, Sofia entered into a marriage of convenience to Vladimir Onufrievich Kovalevskaya, a paleontologist in 27 September 1968 at the age of 18. So this marriage of convenience is a paper marriage where you don't do the marriage physically. It's just a fake marriage. It's also called a phase marriage. So at the age of 18, to study mathematics, she has to go into a marriage of convenience or a fake marriage with one gentleman, Vladimir Onufrievich Kovalevskaya. So in 1878, they had a daughter, Sofia, nicknamed Fufa. Though it was a marriage of convenience, but after some time, they fell into love, and this marriage of convenience turned into a real marriage. And so they had a daughter whose nickname was Fufa. So this is a time where Sofia was getting married. And this is a daughter Fufa, with the daughter Fufa. After spending some years together as a couple, Vladimir, financially ruined, a victim of depression and unable to support his wife and daughter, committed suicide on 15 April 1883. You can see a tragedy over there. So this was the Soviet time of Vladimir Kovalevsky, the husband. He was a paleontologist, so that is why the Russian government or the Soviet government has decided to have a postage stamp of 40 kopeck. In 1970, Sofia decided that she wanted to pursue studies under Karl Weierstrass from Germany at the University of Berlin. Sofia studied under Weierstrass for 4 years. So her major achievements were done when she was studying with Karl Weierstrass in the University of Berlin. This is Karl Weierstrass, 1815-1997. Doctorate degree. It's a very strange type of doctorate degree. By the spring of 1874, Sofia had completed 3 papers. Weierstrass deemed each of those worthy of a doctorate. The 3 papers were one was on the theory of partial differential equation. Another paper was on the reduction of a certain class of abelian integrals of the 3rd rank of elliptical integrals, and the third one was supplementary remarks and observations on Laplace research on the form of Saturn's ring. That is application of mathematics in astronomy. So Weierstrass thought that even one paper is worthy for a doctorate degree. In 1874, Kovalevskaya was granted her doctorate. Summa cum laude means the highest one, from Göttingen University in Germany at the age of 25 in absentia. So she don't have to defend. On the work of her paper, she was awarded a doctorate degree.
The time is 6 p.m. Hello.
So this is the time when she got the doctorate degree at the age of 25, very young. Her paper on partial differential equation won her valuable recognition within the European mathematician and was her doctoral dissertation. So of the 3, the work on partial differential was taken as the paper for her doctoral dissertation. It contains the Cauchy-Kovalevskaya theorem, which gives condition for the existence of solutions to a certain class of partial differential equation. Now this Cauchy-Kovalevskaya theorem is very important. A lot of people use it. And after obtaining a doctorate degree, she came back to Russia. Sofia Kovalevskaya and her husband returned to Russia after she earned her doctorate degree, because when she has to go abroad, she couldn't go alone. So she had to have a husband or her parents. So that's why she made a fake marriage, but they fell in love, as I've told. Sofia was unable to find the academic position she desired. So when coming back, she wanted to She already had a PhD degree, doctorate degree. So she wanted to become a faculty at a university, but she was not granted. So at the time, it was the Tsar regime. The Tsar were there, just like our kings Orlik. So Tsar then refused to give her any position in university, but Tsar requested her to go to a school uh, as a teacher. She directly refused it. She said that I don't understand school mathematics. I only know university mathematics, and she refused to work in any school. These are some of the notes uh, of Sofia Kovalevskaya. So what are her achievements? Of course, one of the achievements is having a doctorate degree in absentia on the basis of her scientific work. During her career, she published 9 research papers, about 3 I have already told, dealing with topics such as the propagation of light in a crystal, the shape of the rings of Saturn, the laws of describing rotations, and works pertaining to theoretical issues in partial differential equations. So our work was more of practical application of mathematics, especially partial differential equation. So this is a clipping from the London News, the listed London News, uh, on August 9, 1884. This lady, a native of Russia, is a celebrated mathematician who lectured last winter in the University of Stockholm and who has just been appointed professor of mathematics in that university. We believe that this is the first time since the Middle Age in Italy that a woman has been appointed to an academic chair at any university in Europe. Sweden is a country where much interest has been felt in the claims of the pure sex to a full opportunity of acquiring and exercising intellectual accomplishment. The person now concerned to Maryam Kovalevskaya is worth of notice as a sign of the times and will be observed with gratification by the many English friends and advocates of higher education for women. So about the work, our work in Sweden, I will come now. So from 1883 to 1889, she was in Sweden. In 1883, she received an invitation from an acquaintance from former student of Westras, Gustav Mitagliafer, to lecture at the University of Stockholm. She was able to secure a position at Stockholm University in Sweden. 11 February 1884, delivered the first lecture at the Stockholm University. In 1884, she was appointed to a 5-year position as Professor Extraordinarius, that is, Professor without chair, and became the editor of Acta Mathematicians. So she was the first lady editor of any scientific mathematics journal, and the journal was Acta Mathematica. She was elected corresponding members of the Russian Academy of Sciences within that period when she was still in Sweden. She obtained the prize of the Stockholm Academy from Sweden, and publication of Memoirs of Childhood in Stockholm. She published it, and this memoir was written with the title Nihilist Girl. In 1889, she was appointed Professor Ordinarius at Stockholm University, the first woman to be hold such a position at a Northern European university. And as I have told, in 1990, she wrote her biography when she was working in Sweden. So the title of this novel was Nihilist Girl. The book, it looks like this one. You can see, written by Sofia Kovalevskaya. Now coming to the prize. French Academy of Sciences was created in 1966, one of the oldest academy. It is an assembly of scientists chosen from among the most eminent French and foreign specialists. It also supports research and encourages scientific life on an international level. It's not really for the French, so it can go beyond the boundary to any country. In 2016, the Academy celebrated its 350th anniversary. Today, it has 279 members, 105 foreign associates, So you can see there are only 5 foreign statutes and 66 correspondents elected from among the most eminent French and foreign scientists. It is multidisciplinary and widely open to the international market. But you see, it was very conservative, this French Academy of Conservative. So out of the so many members, there were no female members until 1980. In 1980, Marguerite Yourcenar was the first female member elected to the Academy. So in 1980, I was in Paris at the time doing my PhD, but spending some of my vacation times in Paris in the news and in the newspaper in 1980, I came to know that this French Academy of Sciences had its first female member. Now coming to the Prix Bordin given by this academy. The Prix Bordin was created by Charles Laurent Bordin by his will, dated April 7, 1835. The Prix Bordin was the second most prestigious in a very long line of awards given out by the French Academy of Sciences. There's a great prize known as Great Prize over there. The French Academy has a great prize. Now this is the second one called Prix Bordin. The chosen topic for 1888 was improve in some important point the theory of the movement of rigid body. So it's time when they announce the prize, they choose a topic and make announcement of the prize and pay, and they invite the work on this line. The entry for the prize was to be put in a sealed envelope with a slogan of the author's choice. So on the envelope, you also have to write down your own slogan. The manuscript was to be submitted by 1st July 1888. 15 manuscripts were submitted to the competition. She entered her paper for a Prix Bordin in title. The title she has given to the work was On the Rotation of Solid Body about a fixed point. While submitting her work for a Prix Bordin, Prix is prize in French language, she wrote the slogan on the envelope: say what you know, do what you must, come what may. So you don't bother about the results. Come what may. Stay what you know, do what you must. On 18 December 1988, Sofia Kovalevskaya was informed about the winning of the Prix Bordin. On 24 December 1984, after 1 week, the official presentation of the diploma took place. The paper was so highly regarded that the prize money was increased from 3,000 francs to 5,000 francs. So that work was so nice work. And so the prize money was increased from 3,000 to 5,000 francs. On 18 December 1988, Sofia Kovalevskaya was informed of the winning of the Prix Bordin. On this, so I am also going to show this copy of the diploma in the next slide over here. So this is the copy of the diploma. Over here you can see Madame Sofia Kovalevskaya. This is Institute de France over here. So this is the copy of the diploma which was given to her on 18 December 1888. So everything is 18 there, 18 December 1888. This subject has been considered before, most notably by Leonard Euler and Joseph Louis Lagrange, that is rotation of the solid body. Euler derived the equation of motion, but considered only the special case where the center of gravity of the body coincided with a fixed point. Lagrange considered a case where the center of gravity of the body lay on the same axis as the fixed point. So these two people had some restriction on the equation of the motion of solid body. Sofia considered the cases of an asymmetric top where the center of gravity lay in the plane perpendicular to the axis of rotation, and the fixed point was the point where the plane and axis intersect. So she has advanced equation, and so it was a very nice paper and practical one. Our greatest achievement in mathematical research in our paper on the rotation of solid body with a fixed point. A top is one example of the type of objects being studied. They are gyroscope and pendulums and planets, suns, moons. So that equation can be used for all these type of motions. So you can see here it's just the rotation of a top. Oh, it goes like that. Champati kumaune bhन्छ नि हामी नेपालबाट. It's something like this. This is the work she has done. Our equation is related with such a motion. On 10 February 1891, Tuesday, Sofia Kovalevskaya died of pneumonia in Stockholm, Sweden, at the prime age of 41. Actually, she was traveling from Europe, Central Europe, that is Germany, and France, and from there she was going to Stockholm, and February was very cold time, and she got the pneumonia and died on February 10, 1891 at the age of 41. Sofia Kovalevskay's grave is in Sweden, Norra Begravningsplatsen in Stockholm, Sweden. This is her grave in Sweden. Unfortunately, I have not visited that place. I have been to Sweden, but I have not visited that place. So let's quickly look at what is the most important theorem called Cauchy-Kowalevski theorem. It is the basic proof of the existence of analytical solutions of analytical differential equation. For a general differential equation of order m in several variables x1 to xn, Cauchy formulated a boundary value problem that is called Cauchy's problem to find a solution of the equation with Cauchy initial data of order less than m on a given surface. So Cauchy has taken a general differential equation. The problem makes sense only when the equation gives a normal derivative as a function of the others. If we introduce coordinates such that S is the plane xy, x1 is equal to 0, which is to say that the equation can be written as a partial differential equation now. So ordinary differential equation has been now converted into partial differential equation, where terms of left does not appear among the derivatives of m, the partial derivative of m of the terms on the right. In an equation of this form, we can calculate by differentiations all the derivatives of a solution u restricted to S, where the Cauchy data is known. Kovalevskaya shows that the formal solution calculated in this way is analytical at a point x0 on when x1 is equal to 0, as I have stated. If the Cauchy data is analytical, and in addition, the function g is analytic for the values of the derivative u and all the partial derivatives corresponding to the Cauchy data at the point. So Cauchy has given the ordinary differential equation. Kovalevskaya converted into partial differential equation, so that it can be applicable in many fields. So it is rotation of a solid body of a fixed point it is a classical problem on which Euler, Lagrange I have shown, and plenty of others has worked. It has to do with studying the movement of a solid mass, just like over here, solid mass over here, massive body in a constant gravitational field with a fixed point. So some point are fixed over here. This movement is, of course, governed by differential equation, a rather complicated system of differential equation. So if you try to write a differential equation, it's become very complicated differential equation. So just like this one, you can see a very complicated differential equation. The unknowns here, PQR. So PQR here, you can see PQR here. The coordinates of the instantaneous rotation vector, gamma 1, gamma 2, here it is over here. Coordinates of gravitational field are the vector x0, y0, z0. Here you can see this is x0, y0, z0. It is the fixed point to the center of gravity. The positive numbers A, B, and C, you can see A, B, C are here. A, B, C are the elements of the inertia, where it is calculated with a double integral over here. The differential equation is complicated, as I have already told. Moreover, at the moment Sofia attacked it, the problem was left over from the 18th century, and the work of Euler and Lagrange had worked on it, but they couldn't tackle it to the end. No one knew how to solve it except in two cases, which I have told. One is when the Euler's case and the Lagrange case over here. So Sofia noted that in Euler and Lagrange cases, the solution of system are meromorphic functions of time and asks whether this property holds in the general case. So what is a meromorphic function? A meromorphic function is a function of complex variable. It is thus that Sofia came to consider time as a complex variable, an idea that was surely more in the air in the second half of the 19th century than it was in Euler's time. So Sofia Kovalevskaya solved the problem, real problems, by using complex variable and converting ordinary differential into partial differential equation. It is a function that has poles. A pole is a value of the time for which the sum of the functions that enter into solution becomes infinite, as in the case of the function t tends to 1 by t square. You can see it tends to infinity over here, whose graph is shown here. It is therefore the case that there are values of time for which the solution blows up, and these are values no one has ever seen. They are imaginary and not real. So Sofia Kovalevskaya has used imaginary numbers to solve the real problems. So we observe the existence of invisible singularities for solutions that do not have real values. It is implicit in that the solution of such a differential equation generally have singularities that are more complicated than simple poles. The way in which Sofia approaches the problem is then to ask, is it the case that this simplicity of singularities occurs for other forms of the solids? She asks, for what values of the inertia matrix, that is the constant ABC, and which position of fixed point x0, y0, z0 do the solution possess? She actually achieves expressing the solution in terms of theta function in two variables. So theta function is also a complicated function. The commission that awarded the prize brought up first and foremost the use of theta function in two variables, for it was the first time that these functions had been used to solve a problem outside of function theory. The title of the prize problem was Perfecting an Important Point in the Theory of Motion of a Solid Body. Okay, so that is how work was so solid that the prize money was raised from 3,000 francs to 5,000 francs. Some quotes of Sofia Kovalevskaya. It is impossible to become a mathematician. It is impossible to become a mathematician without being a poet in soul. It seems to me that the poet has only to worship that which others do not worship, to look deeper than other looks, and a mathematician must do the same thing, just like a poet. Many who have had an opportunity of knowing any more about mathematics confuse it with arithmetic and consider it an arid science, dry science. In reality, however, it is a science which requires a great amount of imagination. This is a photo of Sofia Kovalevskaya from 1899. Now, coming to my thesis, I have already shown some of these photos. So my PhD thesis, which I defended on May 1983 in Moscow, in People's French University. So I'm defending, at a time, we have to write all this formulae over here and defend it in the presence of 24 professors. There's a jury of 24 professors. This is my supervisor, and there are some Nepali students, some of my colleagues listening to my defending. So it's a very tough defending, but I have shown this photo because from my thesis, 1983, I have told earlier also, I entered into PhD thesis in September, PhD work in September of 1980 and completed in May 1983. That means in 2 years, 8 months and 19 days. On the following pages, I have copied page 39 and 40 from my PhD thesis. The title of my PhD thesis was Construction of Equation in the Form of Lagrange, Hamiltonian, and Birkovian according to the precise properties of motion. What I have done is Lagrangian and Hamiltonian is known to us. So I have introduced the Birkovian system, which under certain conditions turns into Lagrange, or in certain terms turns into Hamilton. So that I have generalized Lagrange and Hamiltonian with the help of Birkhoff. The thesis was defended on 19 May 1983 in a specialized council at the People's Friends University named after Patrice Lumumba. Anyway, now let me show this page 39 and 40 of my thesis. So this is the page 39. You can see written in Russian, but these equations I wrote on myself using rotary drawing pen over here. So typing such a thesis was very difficult because you have to put the space as required. Somewhere 4 equations, 5 equations are there over here. But my emphasis is here on the 2 red ones. It is in Russian, but it is a Cauchy-Kovalevskaya theorem. So I have used Cauchy-Kovalevskaya theorem, which show that there exists, this solution exists for my problem over here. You can see the Cauchy-Kovalevskaya is here. Okay. So in mathematics, the Cauchy-Kovalevski theorem is the main local existence and uniqueness theorem for the analytical partial differential equation with Cauchy initial value problems. A special case was proven by Augustine Cauchy and a full result by Sofia Kovalevskaya. Now some 3 books to Kovalevskaya. The lunar crater Kovalevskaya is named in her honor. It is located on the far side of the moon facing west. And in St. Petersburg, in Moscow, we have streets named in honor of Sofia Kovalevskaya. And there are several postage stamps after her. So one was issued in Soviet Union by 1951. Okay, see, it's a very simple one. It's 40 kopek only, but this one is the Russian one, 1,500 rubles, very big one, 1996. So the sources I have taken to make my presentation these are the books which is lying in my shelf over here. This is the main book I have used is this, the biography of Sofia Kovalevskaya. You can see this photo I have used over here. And I have a Russian book which is called The Prominent Scientist or Mathematician over here. So from here, there's a big one chapter on Sofia Kovalevskaya. And also I have an English book by Michael Odin, Remembering Sofia Kovalevskaya. Is a Springer publication over here. So these books which I have shown is lying with me. Now, so that is about Sofia Kovalevskaya. Now, since I have used the Prix Bordin, which is given by the French Academy of Sciences, then the remaining part is the Hilbert's 23 problems. So every mathematician should know about the 23 Hilbert's problems, and also is aftermath of this Hilbert's 23 problem. So what is Hilbert's problems? Since 1900, ICM, International Congress of Mathematics, takes place every 4 years. The last one was 2018. This ICM 1900 was held in Paris, France, from 6 to 12 August 1900. It was in this ICM 1900, David Hilbert, Germany, presenting his 20 famous problems under the title Schur's Problems, Futuristic Mathematics, on the future problems of mathematics on 8 August 1900. Though David Hilbert was a German, but this ICM 1900 in Paris was held under his patronage. He was the chairman of this ICM 1900. And so he has the privilege to give the mathematical problems lecture delivered before the International Congress of Mathematics at Paris in 1900 by Professor David Hilbert. So I have downloaded all his presentation over here, but I will not go through his present daily lecture. I'll just show the 23 problems. So I have all his lecture over here. Now let's go to the Hilbert problems. First one of 23, the first is set theory. So Hilbert thought that within a century, starting from 1900, within a century, these 23 problems will be solved by prominent mathematicians. The first one is set theory. On set theory, the problem was on continuum hypothesis, well-ordering principle. There is no set whose side is strictly between that of the integers and that of the real numbers. This is what is meant by continuum hypothesis. It was proven to be impossible to prove or disprove in 1963. It was proven to be impossible to prove or disprove this hypothesis. The second problem was consistency of arithmetic axiom. The arithmetic is a formal system that does not prove a contradiction. It has been only partially resolved, so it's still not been fully resolved. Or one, equality of volumes of two tetrahedron of equal base area and height. So two tetrahedrons which has equal base and height, whether their volumes are equal or not. Can two tetrahedrons be proved to have equal volume? Result, no. They are not of equal volume. Proved using Dehaene invariant. The fourth problem was shortest line between 2 points. Construct all matrices where lines are geodesic. Because in a plane, we have this straight line to join 2 points. But in a other dimensions, if you in 3 dimensions or in or hyperbolic or parabolic type of spaces, then construct all matrices where lines are geodesic. Too big to be stated, resolved or not, we don't know. So it is still an open question. Tip 1. The groups and differentiability of this function. That means, are continuous groups automatically differential groups? Resolved by Andrew Gleason in 1953. Sixth one is mathematical treatment of the axioms of physics. Axiomize all of physics. Unresolved, not mathematical because it is related with physics, more with physics. It is axioms of physics. So it is not mathematical. Seventh one, irrationality and transcendence of certain numbers. We already know that there are some certain transcendental numbers like pi and e. Is a to the power b transcendental for algebraic a not equal to 0, 1 and in irrational algebraic b? A is algebraic and b is irrational algebraic. Resolved. Yes, the result is yes, illustrated by Gelfand's theorem. So after some time in my seminar series, we will also come across Gelfand. Eighth one is prime number problem, Riemann's hypothesis, distribution of primes, which is a very prominent problems tackled by a lot of mathematicians. The real part of any non-trivial zero of the Riemann zeta function is half. Every even number greater than 2 can be written as a sum of 2 prime numbers. This is prime numbers problem. Open. It's called Goldbach conjecture. At the end of this lecture, at the seminar, you will see this Goldbach conjecture. It's still open. Ninth problem is general reciprocity law in algebraic number theory. That is, find most general law of reciprocity theorem in algebraic number field. It has been only partially resolved. 10th problem is decidability of solvability of Diophantine equation. So Diophantine equation is it is so primitive and is still going on. Determination of all the solvability of a Diophantine equation. Diophantine equations are equations with integer coefficients. Resolved. No, you can't determine of the solvability of Diophantine. Diophantine equation can't be solved in totality. 11th problem is quadratic forms with algebraic number coefficients. Solving quadratic forms with algebraic number coefficients. Partially resolved. 12th, generalized theory of field extension to arbitrary rational numbers. Extended Kroneker's theorem on abelian extension of the rational number to any base number field. It's still open. 13th problem, possibility of solving a general quantic means fifth power, so seventh power. Solve all seventh degree equation using function of two parameters. Resolved by Vladimir Arnold based on work by Andrei Kolmogorov. These are Russian mathematicians. So it was solved in 1957. In 14th problem is invariant and covariant of rational function systems. Proof of the finiteness of certain complete system of function resolved negatively by Masayoshi Nagata, Japanese, in 1959. In problem, rigorization of enumerative geometry, rigorous foundation of Schwarz's enumerative calculus. It has been only partially solved. 16th problem, topology of algebraic curves and surfaces. Maximum number of limit cycles is the problem. It's open. It's called Poincare conjecture. So it is still open. Once it has not been solved, it still remains as a conjecture. 17th problem, reduction of quadratic forms to sum of squares. Expression of definite rational functions as a quotient of sum of squares. Resolved by Emil Martin in 1927. 18th problem, filling space with congruent polyhedra, that is function definable from differential equations. Is there a non-regular space-filling polyhedron? What is the densest spare packing? Resolved by Karl Reinhardt in 1928. 19th problem, analytic solution of problems of calculus of variation. Are the solution of Lagrangian always analytical? Resolved positively by Ennio de Giorgi, most probably Italian, in 1957. 20th problem, general solution of Dirichlet's problem. Do all variational problems with certain boundary conditions have solution? Resolved, but not shared. 21st problem, monodromy groups over differential equations. Proof of the existence of linear differential equation having a prescribed monodromic groups. Resolved. 22nd problem, relation between automorphic functions. Uniformization of analytic relations by means of automorphic functions is also resolved. 23rd, the last one is solubility of problems in calculus of variations with one or several functions and integral. You can see the last 3, 4 are related with calculus of variation. Further development of the calculus of variation, it is also resolved. But some of these which hasn't resolved, I don't have the data who has resolved it. It must have been a work of group of mathematicians, a few mathematicians. So the final count is like this. 13 of the 23, 13 has been resolved, 4 has been partially resolved, and 6 is still totally open. So this is the Hilbert problem. Hilbert thought that within a century, all the 23 problems will be resolved, but only 13 of them has been resolved. So still there are 10 to be resolved. But now we are in 21st century. That was for 20th century problem. Now we are in 21st century. Now for 21st century, we have other type of problems. So there are some research, just like for this France Academy of Sciences, they award this called research is called awarded research, because if the topic is given and if the research is completed, you get a certain financial award also. Of course, recognition and financial award. In 1997, an article in the Times of London was published by the publisher. Faber and Faber are the publishers over there. They published, and they said that Faber offered a $1 million prize for solution of the Goldbach conjecture. So you can see Goldbach conjecture is still unsolved. So if anybody can solve this Goldbach conjecture, so this favor will give you $1 million. So that's what we mean by award research. In a letter to Euler, dated June 7, 1742, Goldbach conjectured that every even integer greater than 3 could be written as a sum of two prime numbers. Very simple this conjecture, Goldbach conjecture, very simple. That every even integer greater than 3 could be written as a sum of two prime numbers. There was one more award research in 2000, because 2000 is the World Mathematical Year. On May 24, 2000, author Michael Jeff, he is the president of Clay Mathematics Institute. He was also the president of American Mathematics Society in 1990s. So on May 24, 2000, author Michael Jaffe, president of the Clay Mathematics Institute, announced the Million Grand Challenges in Mathematics at a meeting held in the Collège de France in Paris. So what is this Clay Mathematics Institute? The proof or a counter example to 7 important world mathematical conjectures would earn a $7 million award with $1 million for each of the answers. So there are 7 mathematical problems, each carrying $1 million as the award. So let's see what is this Clay Mathematical Institute. In 1985, author M. Jaffe became the head of department when George Mackay retired from the Harvard Mathematics department. So Jaffe became the head of department. June 14, 1998, in the graduation ceremony, author Jaffe approached a donor and a Boston businessman, Clay, Landon T. Clay, for sustainable fund to assist in the implementation of some new ideas to boost the mathematical research at the department, including Prize 2000. 2000 is the World Mathematical Year. So on August 1998, ICM in Bordin, International Congress of Mathematics in Bordin, author MJ discussed with Andrew Wiles. Andrew Wiles is the mathematician who solved the Hilbert's last year, the probable creation of new foundation for mathematics. On September 25, 1998, CMI became this Clay Mathematics Institute became a corporate entitled entity registered in the state of Delaware, US. On October 27, 1998, Landon T. Clay, who was the donor, transferred share of stock to create the CMI, Clay Mathematics Institute. May 10, 1998, a set of public lectures at MIT marks the formal opening of CMI. On April 10, 2000, CMI Scientific Advisory Board approved the 7 problems and the $7 million, which is called Million Challenges. It's called 7 Million Challenges. May 24, 2000, CMI announces the Million Challenges problems at the Collège de France. The Million problems are the hardest and most important unsolved mathematical problems in the world. So Hilbert's 20 problems were for 20th century. Now these $1 million prizes are for the 21st century. They have registered numerous attempts at solution over many years by the best mathematical minds around. The 7 million prizes problems are the current Mount Everest of mathematics. So what are these $7 million prizes? Each one which carries $1 million award. Number 1, the Beach-Swinnerton-Dyer conjecture. The problem was posed by Andrew Wiles. In the bracket are the mathematicians who has posed these problems. The Beach and Swinnerton-Dyer conjecture asserts that the size of the group of rational points is related to the behavior of the associated zeta function near the point s is equal to 1. Second, the Hawes conjecture proposed by Pierre Deligne. The Hawes conjecture asserts that for particularly nice types of spaces called projective algebraic varieties, the pieces called Hawes cycles are actually a combination of geometric pieces called algebraic cycles. The third one, the Navier-Stokes equation as smooth solutions proposed by Charles Fairman. Although these equations were written down in the 19th century, our understanding of them remained minimal, very small. The challenge is to make substantial progress towards a mathematical theory which will unlock the secrets hidden in the Navier-Stokes equation. Fourth one is P is not NP, proposed by Stephen Cook. Stephen Cook and Leonard Levin formulated that P easy to find versus NP easy to check problem independently in 1971. The Poincare conjecture proposed by John Miller. This conjecture is called the Hilbert's problem number. It was in the Hilbert's problem number 6 among the 23. It's number 16 related to topology of algebraic curves and surfaces. Henry Poincare suggested that anything without holes had to be a sphere. If the simple connected closed three manifold is homomorphic to the three sphere. The fifth one, the Poincare conjecture, also proposed by John Miller, who said that this conjecture is related to Hilbert's problem number 16, related to topology of algebraic curves, solved by Russian mathematician Grigory Perelman in 2003, but he refused to take this $1 million. So when he was approached here by ICM, this MCY, and they went there to Russia to meet him, but he refused to take the prize. He said that I am a very simple man. If I take this $1 million, I'll be spoiled and ruined. I'll stop doing mathematics. So he refused to take the prize. So born in June 13, 1966, very young person, mathematician. One is quantum Tang-Mill theory exists with a mass gap proposed by Arthur Jeffrey and Edward Region. Almost half a century ago, Young and Mills introduced a remarkable new framework to describe elementary particles using structures that also occur in geometry. The successful use of Young-Mill theory to describe the strong interaction of elementary particles depends on a subtle quantum mechanical property called the mass gap. The last one, the Riemann hypothesis, proposed by Enrico Bengueri, Italian professor. This Riemann, 1860s, observed that the frequency of prime numbers is very closely related to the behavior of a elaborate function, the zeta function, you can see that, called the Riemann zeta function. The Riemann hypothesis asserts that all interesting solutions of the equation Z, that is the solution, Z is equal to 0, lie in a certain vertical line, actually half, minus half, half over. So these are the $7 million problems. So September 22, 2000, in the World Mathematical Year 2000, talk program was organized in the Central Department of Mathematics TU in Kirtipur during our World Mathematical Year 2000. And the talk was given by Dr. M. Bogosky from People's Friendship University of Moscow. He gave a brief description of a third millennium problem, that is Navier-Stokes problem, and elaborated on him. So when we listened to his problem, I thought that Bogosky may be a $1 million problem owner, because he has so described about this talk on the talk of this third million problem, that is Navier-Stokes problem. So this is the photo when he was delivering the speech at the Central Department of Mathematics in 2000. Dr. Bogosky was an external examiner for the PhD defense of Dalbar Adhikari at KU Dhulikhel, because when Dalbar had to defend his PhD thesis, then we didn't find a proper supervisor over here. So we have to bring the external examiner from Russia. So Dr. Bogosky came as an external examiner for the defense of Dalbar's thesis. And in 2000 itself, in September, he got the PhD degree, and you can see the supervisor and the external examiner there at the KU premises there during the convocation. So I made a presentation over here. Actually, this COP you have seen, I have given here on February 5, 2015 when I was visiting Moscow. Now, briefly coming to an end, briefly on the Goldbach conjecture, which is, it looks very simple and which is still open. Goldbach conjecture is the eighth problem of Hilbert. Though it was still an open problem, it was not one of the million problems. It was a very nice conjecture, but it was not included in the 7 million problems. But it was in the Hilbert's eighth problem. Goldbach conjecture is one of the oldest and best known unsolved problems in number theory and in all of mathematics. It states that very simple statement is there. Every number greater than 2 can be, every even number greater than 2 can be expressed as a sum of 2 primes. The conjecture is divided into two parts known as the weak and strong conjecture respectively. The conjecture that has additions since Goldbach's original theory was presented. George Musser on January 2003 in Scientific America writes, since science operates according to the law of conservation of difficulty, the simplest question has the hardest answer. So always the simplest question has the hardest answer. To get an easier answer, you need to ask a more complicated question. Goldbach originally described his conjecture in a letter to Leonard Euler in 1742. So let's look at this letter, which is written like this. Every number greater than 5 can be written as a sum of 3 primes. 3 primes. The original Goldbach conjecture is every number greater than 3, every even number greater than 3 as a sum of 2 primes. This is now a bit different one. Every number greater than 5 can be written as a sum of 3 primes. This is a weak one. Every even number greater than 2 can be written as a sum of 2 primes. This is the stronger conjecture. For example, all the even number, 4 can be written as 2 plus 2. 6 can be written as 3 plus 3. So this prime numbers can be repeated. 8 can be written as 3 plus 5. 10 can be written as 3 plus 7, or you can write as 5 plus 5. 12 can be written as 5 as 7. 14 can be written as 3 plus 11, or 7 and 7. And so in this way, this is example of Goldbach conjecture looks through. 54 can be written as 7 plus 47, 11 plus 43, 13 plus 41, 7 plus 37, and 23 plus 31. You can see these are all prime numbers over here. So any even number greater than 3 can be written as the sum of 2 prime numbers. This is what is Goldbach conjecture. So this is a photo of Goldbach. This is David Hilbert, about which we have been talking in this second phase on Hilbert's problem. This is the one of the book I have used in my preparation of this second part of lecture, the Princeton Companion to Mathematics by Timothy Gross. This book can be downloaded freely. So I have downloaded and I have binded it in a very nice way. So I am using this, the Princeton Companion to Mathematics. So I request that you please download it and put it as a copy in your library. So this concludes our today's seminar. Next seminar will be on October 1, 2021. So I have completed 3 plus 0, S0, S0, S1, S2, S3 in September. So we'll have some more seminars in October, because in October we have this Dasai coming. So it will not be 3, 4, 5, like I said, 3, 4, 5. So it may be limited over there. So next seminar will be on October 1, 2021, S4. And the title of next time's seminar on the series Mathematics 3 Days will be From Zero to Infinity, What Makes Numbers Interesting. So the very title, so that next seminar will be more interesting over here, because talking of mathematics from 0 to infinity is a very lot one, but I'll try to finish within 1.5 hours, just as I'm doing within this series of my talks on mathematics theories. Okay, thank you very much. If there are some questions, you are welcome. Okay.
Okay, thank you so much, Bhadra Man sir. So the floor is open. I think if you have any questions, queries, you can ask with Bhadra Man sir.
So you can see that almost in all of my presenters seminars, you will see at least one photo where you will see me there. To show
Yes.
that how I have been so much closely associated with all these activities.
That's interesting, sir. So
Because my one of the aim is, of course, to talk about the history of mathematics, but also to motivate that our friends over here who are listening to my seminar will be motivated to participate more and more in such mathematical activities.
so well, I think so. Our participants, have don't have any questions or queries to interact with Bhadraman sir. I think the concept is very clear, and so for me, this was really a wonderful and insightful session. On a female mathematician, Sofia Kovalevskaya, her work, and some Hilbert's problem. So this is kind of an inspiration probably for us. And so आजको सेसन चाहिँ for more specifically for women who wants to work in mathematics and its development. So history has always been our inspiration. I think the next motivation and the innovation that we want to do in this particular field of mathematics and mathematics education. So for this, we have to work on it, as far as I know. So thank you so much, Bhadraman sir. I think I have seen Balchandra sir, our professor here. So I would like to request Bal sir to say a few words on this ongoing series on history of mathematics and end the session.
After some time, I'll send a PDF file of this presentation.
Sure, sir, sure. After getting PDF file from Bhadraman sir, I will compile it and share it with you. Balchandra sir, are you here? Bal sir? So I think Bal sir is not here. So Bino sir, Namaste Bino sir, are you here? Okay, Bal sir is here, I think. Bal sir?
Okay, Balchandra.
ओके थ्याङ्क यू भेरी मच हामी अन्तिममा आएको हो नि होइन सर
Oh,
Yeah, yes, sir.
thank you.
ओके थ्याङ्क यू भेरी मच आई थिङ्क दिस इज वान अफ दि दिस लेट्स I would like to popularize all of us to popularize this talk because this is very important talk as far as the history of math is concerned because we need to understand गणितमा के भइराखेको छ होइन हामी कसरी यहाँसम्म आएको रहेछौँ अब गणितभित्र पनि विभिन्न क्षेत्र विभिन्न रेस विभिन्न एथनिसिटी जेन्डरको हिसाबले विभिन्न प्रकारको पार्टिसिपेसन छ सो आई थिङ्क वी निड टु एक्चुअली अन्डरस्ट्यान्ड दिस ब्याकग्राउन्ड एकदम सरलाई धेरै धेरै धन्यवाद अब नेक्स्ट विकको टकको लागि पनि सबै साथीहरूले अलिकति हाम्रो कम्युनिटीमा म्याथ टिचरहरू होइन म्याथमा काम गर्ने म्याथको क्षेत्रमा काम गर्ने मान्छेहरूमा चाहिँ यो मेसेज अलिकति स्प्रेड गर्नु पर्यो अरू एकदम भद्रमा सरलाई धेरै धेरै धन्यवाद यो आजको सेयरको लागि थ्याङ्क यू भेरी मच सर
ओके ओके अबका यति मेटेरियल भयो कि म हरेक त्यो 1.5 घन्टाको फुल प्याक नै हो 100+